All right. So last time in the previous part of the video, we paused at deriving that around a stationary point, a function of two variables, the change in the value of a function of two variables can be expressed in the form. So let's say you're at the point x comma y, which is very near to the point x naught comma y naught, and assume that x naught y naught, say x naught comma y naught, is a stationary point, which implies that the gradient of f evaluated at x naught comma y naught is 0. We found, and I'll put a link to the video in case you want to review our discussion back then. So we found that df can be written in the form of a quadratic expression, which has the partial derivatives of f, or rather the second partial derivative of f with respect to x. So twice evaluated at the point x naught y naught times x minus x naught square plus the second partial derivative of y with respect to, of f with respect to y minus y naught square plus a mixed partial derivative of f with respect to x and y, and we'll assume that the mixed partial derivative with respect to x, and then if you interchange the order of the mixed partial derivative with respect to x and or y, it remains the same. And for a more in-depth discussion on this, I encourage you to have a look at the website www.dsigma.in and perhaps register yourself for the course on the Introduction to Differential Calculus. So we have the mixed partial derivative times x minus x naught, y minus y naught. And we will have a factor of 2 here because I've taken a half factor as common. So now the task for us, in order to classify this stationary point further, which means that to figure out whether the point x naught comma y naught is a maxima, minima, it's undetermined, or it's a saddle point, there are two approaches. Now, in this video, what we're going to do is we're just going to look at this particular expression, and we're going to do a bit of algebraic manipulations to write it in a form which contains some perfect squares, and from there, try to make some inferences on what df could be. In a more elegant approach, where we can use matrices in order to write this expression in a form which is easily generalizable also to functions of more than one variable, will require a little bit more work, which we'll undertake in a future video. So for now, we're going to just restrict ourselves to this particular example of a function of two variables. We're going to take the right-hand side, rewrite it in a certain way, and then try to deduce whether the function has a maxima or a minima or something else around the point x naught, y naught. And it's a fairly intuitive approach. This is a more intuitive approach. The other one, using matrices, is more elegant and is easily generalizable, and it's equally useful. So we'll do that in a future video. So before we get to doing that, let me introduce a somewhat simpler notation to write down the terms that we have in the expression. So for a partial derivative of f with respect to x, I'm going to use f subscript x. If I'm going to take a second partial derivative, I'm going to write f double subscript x. Likewise, a partial derivative of f with respect to y, we can write as f subscript y. A second partial derivative of f with respect to y, we can write as f y. And likewise, mixed partial derivatives, say you want to find out dow to f, dow x, dow y, we can write as f subscript xy. And in case it's needed for us to distinguish between dow to f, dow x, dow y with dow to f, dow y, dow x, we can write this latter expression in the form f subscript yx. So we have just interchanged the order of x, y in these expressions, right? Likewise, since we're assuming that the point x is very near the point x naught and the point y is very near the point y naught, I'm going to write x minus x naught as dx and y minus y naught as dy. So with these somewhat simpler notations, we can rewrite df as half. We have fxx dx square plus fyy dy square plus 2 fxy dx dy. Now, one of the things I can do next to write this as some kind of a perfect square, or at least introduce a perfect square into this expression, is I'm going to look at this term, and perhaps take the factor fxx as a common factor. Then we have dx square remaining. And then from here, I'll have 2fxy divided by fxx dx dy. And let's just leave this term as it is for now. So this will be fyy dy square. Now here we have a dx square. We have something which has mixed terms dx dy. So I'm going to add and subtract right here. I'm going to add a term which might look like fxy, f square xy, fxx square dy square. And I'm going to subtract this, the same term. So just to make it a little tidier, I'm going to add this. I'm going to subtract f square xy, fxx square dy square. So that's this particular square brackets. And then we are left with fyy dy square. Now, if you look at this, and these three terms, we can combine them in the form of a perfect square. So just to rewrite this in a cleaner form, we have fxx, and then if I combine these three terms, I can write this as dx plus fxy divided by fxx dy square. So sorry about that. So that gives us, if I square this, I will have dx squared coming from here, fxy, fxx squared, dy squared. That takes care of this term. And then we have 2 times dx dy, fxy divided by fxx. That takes care of this term. So we still have this term remaining, which we can combine with this term after multiplying this with a factor of fxx. So that gives me, now these terms will have dy squared as a common factor. So I can write this as dy squared fyy minus f square xy divided by fxx. All right. So hopefully you can do this algebra a little slowly if in case you feel that we've gone a little faster. Just try it out yourself. And if you notice any error, please feel free to comment below. I'll definitely try to rectify it. For now, it seems okay. So what we found is that the change in the value of the function around a stationary point can be written in the following form on the right hand side. Now notice that we have one perfect square here. So that this is always positive. This is dy squared, that's always positive. So which means that that in order for this expression df to be always positive, if I want to ensure that df is always positive, which will imply that any point fxy minus f of x naught y naught, that's by definition d of x is positive, which means f of x naught y naught, which means that fx comma y is greater than any f of x, than the value that the function takes at x naught y naught, which means you will have some kind of a minima here, right? So if this is x naught y naught, and you step away from it to point x comma y, and you find that the value of the function in any direction that you step away from is higher than the value of the function at x naught y naught, you will have a minima there, right? This is the same idea which we used when we derived the nature of the critical points for a function of one variable. Except that here, there could be different directions where the function might be increasing or decreasing. So we're gonna come to that in a moment. All right, so how do I ensure that this expression is always positive, irrespective of the direction that you take? So one of the conditions we can impose is that, let's say fxx is positive. So supposing this is positive, and simultaneously this expression is positive, which means that fyy is greater than f square xy divided by fxx. Now, if I'm assuming that fxx is positive, this denominator is positive, so I can take it on the other side. This gives me fxx fyy is greater than f square xy. So as long as we ensure that this is true, no matter which direction we step away from the point x naught y naught, we'll always find that df is positive. And that guarantees that the point x naught y naught will be a minima, right? So now notice by symmetry that if I'm ensuring that f subscript x twice, this is nothing but the partial derivative of f with respect to x, or rather two partial derivatives of f with respect to x is positive, by symmetry from this expression, since the right hand side is positive, it requires that fyy is also positive. So tau to f, tau to y square is always positive. So I can add this condition here, and these together constitute the first set of conditions for us to find a minima. So I'll write this down here. So x naught, y naught is a minima if fxx is positive, fyy is positive, and fxx, fyy is greater than f squared xy. Right? So you see that this is a slightly more complicated expression than what we found for functions of one variable. But what I'm going to do now is I'm going to pause and I'm going to end the video here, and I'm going to leave this as a quick exercise for you to work on and find out what is the condition for x naught, y naught to actually be a maxima. Can you derive using the same kind of logic that we worked out right now? Conversely, what happens in other cases? Can you derive conditions for when it's undetermined? Which means that you cannot determine whether there is a maxima or a minima. And what about a saddle point? So I hope you'll comment, give your comments, write your answers in the comment below, and I'll be happy to take up this discussion further and address your comments. So let's see if you find this quick exercise interesting. Thanks for watching. Hope to see you again.